Let us now do a few problems. A 150 kilowatt 3000 volt 50 Hz 6 pole star connected induction motor has a star connected slip ring rotor with a transformation ratio of 3.6 stator by rotor ratio. The rotor resistance is 0.1 ohm per phase and its per phase leakage inductance is 3.61 millihenry. The stator impedance may be neglected. Find the starting current and torque at rated voltage with short circuited slip rings. The necessary external resistance to reduce the rated voltage starting current to 30 amperes. So, we will see how to solve this. You can pause the video and you can try it out for yourself first. Okay. So, we will first write down all of the information that is given. What is the output power? It is given as 150 kilowatt. The voltage at which the motor is operated is given as 3000. Frequency is given as 50 Hz. Number of poles is given as 6. And we have the turns ratio or the transformation ratio of the stator to rotor. This is given as 3.6. And then we have the parameters. Rotor resistance is 0.1 ohm per phase. And the leakage inductance, so L2, not reactance. Okay, so this is given as 3.61 into 10 to the power minus 3 Henry per phase. Okay, so what is the first bit? In the first question, you have to find out the starting current and torque. So first we will draw the equivalent diagram. So since the stator parameters are said to be neglected, we will directly draw only the rotor parameters. Okay. Magnetizing inductance also, since no information is given, we can neglect it. Okay. So since the slip rings are short circuited, we are going to have like this. This is a circuit. Now this is the voltage per phase. Now what about the resistance? This is R2 dash by S, the rotor resistance by S, which is referred to the stator side. And similarly, this is JX2 dash. Okay. So what is R2 dash? R2 we know, R2 is 0.1. This is per phase equivalent circuit. So R2 is 0.1. What will be R2 dash? Referring to the stator side, 0.1 into the stator turns divided by the rotor turns whole square. So NS by NR is given as 3.6. So if you calculate this, you are going to get 1.296 ohms. What about X2 dash? First we will find X2 because X2 is not given. What will be X2? It will be omega times L2. Now omega is 2 pi f into 3.61 into 10 to the power minus 3. Frequency is given as 50 Hz. So this, if you calculate, you are going to get 1.134 ohms. Okay, so these are all per phase parameters. Now we have to calculate referred to the stator side. So this is going to be 1.134 into 3.6 square, NS by NR whole square. Okay, so this you are going to get 14.698 ohms. So now we know the parameters. What about the V phase? We need to find out the current. So this is just like a networks question only. We should know the parameters and the voltage. We can easily find out the current. So V phase will be equal to, whenever a voltage is given, if nothing is mentioned, it is the line voltage, and since it is given a star connected winding, you have to take the phase voltage to be 3000 divided by root 3 volt. Okay. So now you are going to get I phase is same as the line current in star connection. So current is equal to V phase divided by root over, we are only talking about the magnitude here. So R2 dash by S whole square plus X2 dash whole square. Okay. Since the question is about starting, we have to find out the starting current and torque. So at starting, what will be the value of slip? It is going to be equal to 1. So here S is equal to 1, since we are finding out the starting current. Okay. So I phase is going to be equal to 3000 by root 3 divided by root over 1.296 square plus 14.698 square. Okay. So this, if you calculate, you're going to get 117.38 amperes. So this is the starting current. We also want to find out the starting torque. So what is the expression for starting torque? T is equal to 3 by omega s into I2 dash whole square R2 dash divided by S. Okay. So what are all the parameters here? S is equal to 1. What is omega s? This is the synchronous speed in radian per second. So this is 2 pi into ns. Now ns in turn, it is dependent on the frequency and number of poles. So the frequency is given as 50 hertz and the number of poles is given as 6 poles. Okay. And what about I2 dash? This is nothing but the starting current that we just found out, 117.38 amperes. And finally R2 dash is also known, it is 1.296 whole square. So if you put all these parameters in this expression, then the torque value you are going to get. So this is 511.59 Newton meter. So this is the starting torque. Okay. So this is the first question. What is the second question you have? You have to find out the necessary external resistance to reduce the rated voltage starting current to 30 amperes. So that means when the rated voltage is given, we want to reduce the starting current to limit the starting current to 30 amperes. So in that case, what should be the external resistance? So external resistance will appear in series with these parameters. Okay. So what will be the equivalent circuit in that case? Second bit, you're going to have R2 dash by S. This is JX2 dash, and here you're going to have external resistance referred to the stator side, remember. Okay. So we have to find R external, not R external dash. So this is given to V phase. V phase, we know it is 3000 by root 3, the rated voltage. Now I phase, we want it to be 30. So if I phase is 30, what will be the impedance that we can see from here? It is equal to V phase by I phase. So this is 3000 divided by root 3 divided by 30 amperes. Now what is the impedance? This is equal to R2 dash by S plus R external dash whole square, the total resistance whole square, plus X2 dash whole square. This is equal to 3000 by 30 root 3. So if you square on both sides and substitute the X2 dash and R2 dash values, what are you going to get? R2 dash by S plus R external dash is equal to 55.832. Now here S is equal to 1. Okay. So R external dash, you're going to get 55.832 minus 1.296. So you're going to get 54.536. Okay. So what will be the actual resistance value? This is going to be 54.536 into n R by ns whole square. Okay. So that means 54.536 divided by 3.6 square. So if you calculate, you're going to get 4.208 ohms. Okay. So this is the external resistance you need to add so that you can limit the starting current to 30 amperes. Next question we have a 3-phase 10 kilowatts 400 volt 4 pole 50 hertz star connected inductor motor draws 20 amperes on full load. Its no load and blocked rotor test data are given below. So no load test data is given as 400 volt 6 ampere 1002 watts. Blocked rotor test 90 volt 15 ampere 762 watts. Neglecting copper losses in no load test and core losses in the blocked rotor test, estimate motor's full load efficiency. So that means you can try it out for yourself first. So the question that is asked is about the efficiency. That means we need the power information. So what is the various power information, power and losses information that you can get from these two tests? Okay. One important point given is neglect copper losses in no load test. Okay. So that means in the no load test, whatever power is given, that is simply equal to the core losses. So why is that? From the no load test, power drawn or the output power is equal to 0, right? It is not driving any load, that is why it is called no load test. So that means power drawn is catering to the losses. Now the copper losses are neglected in the no load condition. So that means it is simply equal to the core losses. Therefore, the wattmeter reading that you got in the no load test, that gives you the core losses. Okay. So therefore, core losses is equal to wattmeter reading in no load test, which is 1002 watts. Okay. So what are these? This gives the entire 3-phase power, not the single phase. This voltage will be the line voltage, this current will be the average current. That means if all the 3 lines are having the same current, well and good, but if they are having slightly different currents, you will take the average. They should have more or less same currents because it is a balanced phase. And this is 3-phase power. Similarly, in blocked rotor test, this is the line voltage, this is the phase current or the average phase current, and this is the 3-phase power. Okay. So the core losses of the entire 3-phase motor is 1002, not the single phase. Okay. So now we have the core losses. Now what about copper losses? So copper losses information we can get from the blocked rotor test. In the blocked rotor test, here also the power output is 0. The motor is not rotating only. Okay. So there will be no power output. So what will be the power drawn? This will be equal to losses at blocked rotor condition. Okay, so that means the rated current will be flowing. Now this is equal to core losses are neglected in the blocked rotor test. So whatever power is being drawn, this is given as 762 watts, that is the entirely copper losses. So this is copper losses. So you are going to get, therefore copper losses at what is the current? At 15 amperes, because copper losses is dependent on the square of current. Okay, I square R. So this is equal to wattmeter reading in blocked rotor test, which is given as 762 watts. Okay. Now what is the question asked? We have to estimate the motor's full load efficiency. Now what is the full load current that is given here? In the question we have 20 amperes is the full load current, not 15 amperes. Okay. So we have to find out the copper losses at 20 amperes. So you can write, therefore copper losses at 20 amperes is 20 by 15 whole square, because copper losses is dependent on the square of current, into 762 watts, because at 15 ampere it is 762. What is the losses at 20 ampere? So that will be 20 by 15 whole square into 762. So this is going to be equal to 1354.6 watts. So remember, the core losses is independent of the current. So this core losses of 1002, it will remain constant. Now we can easily find out the efficiency. This is equal to, output power is also given in the question. What is the output power? 10 kilowatt. Okay. So we have 10,000 is the output divided by output 10,000 plus losses. So the core losses is 1002 and the copper losses at full load is 1354.6 watts. Okay. So this, if you calculate, you are going to get 80.92%. Okay. So this is the motor's full load efficiency. The next question we have, the blocked rotor current in a 3-phase star connected 15 kilowatts 4-pole 230 volt 50 Hz induction motor at rated conditions is 50 ampere. Neglecting losses and magnetizing current, the approximate blocked rotor line current drawn when the motor is connected to a 236 volt 57 Hz supply is. Okay. So once again, we will first write down all of the information that is given. So we have the power rating. Output power is 15 kilowatts. Number of poles is given as 4. The voltage is given as 230 volts. Frequency is 50 Hz. And the blocked rotor current is 50 amperes. See, the blocked rotor current at rated conditions is 50 amperes. Okay. Now what is the question we have to find out? We have to find out the blocked rotor current drawn when connected to a different supply. The voltage is also changing, the frequency is also changing. Okay. So that means we can take subscript here. This is V1 F1 and I BR1. What is the second case? V2 is 236 volt. F2 is 57 Hz. We have to find the blocked rotor current in this case. So we have to first draw the equivalent circuit, keeping in mind what all should be neglected. Neglecting losses and magnetizing current. So that means we can ignore the resistances as well. So that means this is JX1, magnetizing inductance anyways it is neglected, and this is JX2 dash. Okay. So anyways, this is under blocked rotor condition, so the slip value will be equal to 1. So you don't have to worry about the slip. This is the blocked rotor current and this is the voltage. So in case 1, IBR1 will be equal to V1 divided by omega 1 into L equivalent. Okay. So that means the equivalent together inductance, if you are taking L equivalent, then the frequency, angular frequency into L equivalent will give you the blocked rotor current. What about in this case, I VR2, this will be equal to V2 by omega 2 into L equivalent. L equivalent will remain the same, right? Only the voltage and frequency are changing. So from here you can write IBR2 by IBR1. So this is equal to V2 by omega 2 divided by V1 by omega 1. So this is going to give you the blocked rotor current in the second case is IBR1, which is 50 into V2 by V1. So that is 236 by 230. You can take because by root 3 will be cancelled. So it doesn't matter if it is 236 by root 3 you are writing or you are ignoring by root 3. Okay. And into omega 1 by omega 2, which is simply F1 by F2. So 50 by 57 because omega is 2 pi F. Okay. So if you calculate this, you are going to get IBR2 is 45 amperes.